Good day, everyone. Today, Liao and me would like to talk about week 3 lab that is about analyzing AM modulator and also DSB-SC single carrier modulator. So now for the first question, we are about to see how we can analyze, given inputs, we will analyze the waveform of the modulated signal. So I'll run this. So for amplitude of 0.6 and frequency of 1000, and then for the carrier signal, amplitude of 0.3 and 500,000 frequency. So the M modulation here is 2. The modulation index is 2 as shown here. So we can see this is the waveform of the carrier signal. This is actually many wave, and this is a signal wave. And then we can see from this, the modulated signal, there's this bubble here at the when it go down. So what this shows is that this is the modulated over modulation. Okay, next I would like to talk, because key in will be very long, I would like to talk about the next. So just now the input that I put is according to this 0.6, 1000, 0.3, and 500,000. Next, if we change to 0.3, and if we change the amplitude for the message frequency to 0.3, we can see that the modulation is equals to 1, and then it is a full modulation, so there won't have any modulation here at the bottom half of the waveforms. Next, what if we change the frequency of the message signal? So while maintaining other constants as the same, we can see at 1000, since the modulated signal is m equals to 2, 0.6 over 0.3, so there will be some over modulation. So if we increase the message frequency to 2000, which is, you can see here, is faster, we can see that there will be more of this modulated signal too, according to the frequency of the message signal. Next, what if we change the amplitude of the carrier signal, 0.2 and 0.3? So both of these give different modulation index too. One gives 3 and one gives 2. So as you can see here, the modulation index, because it's larger than 1, this also will have over modulation for m equals to 3. And then if we compare it to m equals to 2, the modulation is much smaller, as you can see here. Next, if we change the carrier frequency signal, the frequency of the carrier signal from 500,000 and between 500,000 and 1 megahertz. So this is 500,000 hertz. This is the modulated signal, and this is a modulated signal. And as you can see here, there is not much difference. This is because the carrier signal frequency is already very high. So the only difference we can see is if we compare to a much lower frequency carrier signal versus very high carrier signal, then we can see the difference in the density of the modulated signal. Next, we would like to talk about proposing a solution, so to analyze the waveform of the frequency spectrum. So I will pass to my teammate Liao to talk about it.
Thank you, Hem. So now for question 2, we use a double sideband suppressed carrier DSP-SC modulation to analyze the waveform and also on the frequency spectrum. And we found out that only the upper sideband and lower sideband are transmitted as shown on the frequency spectrum. This one is for the DSP-SC modulation. Yeah. So thus, from the frequency spectrum, we can know that the DSP-SC modulation consumes less power and provides larger bandwidth compared to DSP modulation during the transmission. And then we also use the SSP modulation with Hilbert transform signal. We found that this transmission uses lesser power and requires smaller bandwidth compared to amplitude modulation and DSP modulation. As we can see that only one sideband is transmitted, shown in the frequency spectrum. This one is for the SSP modulation. Yeah, only one sideband is transmitted. So actually, the purpose of a Hilbert transform signal is to obtain the minimum phase response from a spectral analysis. However, this signal requires the same amplitude, same autocorrelation function, same energy spectral density, and also must be orthogonal 90 degrees to the message signal during the transmission. Thus, SSP modulation is more efficient than DSP modulation. So now we proceed to question 3. Okay, for question 3, we also found out that by changing the value of amplitude signal AM and the value of amplitude carrier signal AC can affect the output signal of the modulator, whereas changing the frequency and phase will not affect it. So this is because that for the modulation index, because the equation for modulation index is M equal to AM divided by AC. Like first example, for our modulation index M equal to 1, which means AM and equal to AC. This is called perfect modulation, as no distortion and no data loss happen. And for M more than 1, which means AM greater than AC, this is called over modulation that causes distortion of the waveform, resulting in data loss. For M less than 1, which means AM less than AC, this is called under modulation, but no distortion of the waveform and also no data loss happened. That's all for us. Thank you.